skeletal animations using assimp. I would like to keep things simple, so I'm not going to create a lot of classes and stuff like that, but rather we will just go through the procedure, and we will see that we can do the animations very easily. Also, we can import and keep those animations using assimp, and also we are going to use GLM for this purpose. Now I am showing this demo in OpenGL, but you don't need to be exactly using OpenGL. You can use this knowledge in dialectics or whatever, or you can also use these things for LWJGL. You don't need to use C++ because assimp is also available there. And let's get started and get familiarized with how we can easily do these kinds of things. So first of all, I'm not going through all of the codes that are not necessary to be explained. Like, first of all, we are just creating a window. Okay, you can create a window. There are tons of tutorials on how you can create a window. I mean, in my case, I am creating an HDL window, and then I am having a loop, a while loop, where I'm just simply checking whether I have to close the window, and if I have to close the window, then I am setting the variable that's value is true, that is running, to false, and that will quit from this loop. And then afterwards I'm just cleaning up the window. So this is very simple in case of just creating a window. Now let's get to the main point on how you can import the model from your file system to the RAM, that is your memory, using assimp. So for that, assimp provide us something called as an importer, assimp : importer. Now assimp is the namespace and importer is the importer, and to use this you need these header file, that is assimp/importer. You also need assimp.post process to do some post processing in the importer, and you just specify those things as flags. And also assimp loads everything in an object called scene, so you also need assimp/scene, and that's probably all that thing that you need to have included in your project from assimp. Now first of all, you need this importer, and then you also have to specify the file from which you are going to load. In my case, I have a model.dai file inside man folder, and then we simply just load the file calling the function importer.read file. And the first parameter to this file is the file path. In our case, our file path is this, and the second parameter is the flags that will help the importer to post process while importing the things. In our case, we are simply just triangulating every face so that we are sure that all the faces are correctly triangulated. And also we are flipping the UVs because in most of the cases the OpenGL space UVs are flipped than normal UVs. And also we are trying to generate smooth normals so that our model looks a bit smooth. That's all. So after you have executed this line of code, you will have a scene, okay, a AI scene called scene, and this scene will hold everything about that model that the file provides, even the camera and all the stuffs. So after you have loaded the scene, you just you just need to successfully check whether there is an error, and it's very easy. You just check whether the scene is returned as a null pointer, or the scenes the flags that are present in the scene, and if they contain any AI scene flags incomplete, or simply if the scene doesn't have any root node, then you just simply put the print the error, or you handle the error. In our case, we are just simply outing, but it's not that matter. Now I exactly know that the mesh I am going to use is situated as at scene m message 0. Now how you can simply load the meshes and all the stuff, you will find tons of videos in YouTube, so I'm not going to go through all those things. But the simple thing is that scene contains all the necessary assets that you need, and there is an array called meshes that contains all the meshes, all the geometries that are included in your model. So in our case, our model has only one geometry, and that is situated as 0 index, and I am taking that model as AI mesh. Okay, so now first of all, we need to understand what kind of data we need. First of all, I am going to show you the data structures that we need. So the first data structure is vertex. Now a vertex represents a point in 3D space, and for that point we are having some properties. One is the position of the point, the second is the normal on the point, the third is the UV coordinate for texture wrapping, and the fourth is the IDs for the bone. And for the simplicity's sake, I have chosen that any vertex can be manipulated using only 4 bones. So I am taking a glm vec4, and these IDs are going to be numbers, but I am taking glm vec4 in case you are using a lower version of opengl and that doesn't support I vec4. But if your opengl version supports I vec4, then go for I vec4. Those are purely integers. In our case, I can just simply go with vec4, and I'm initializing all the values to 0. And also we are having weights associated with each bones, that sum as 1. A vertex can be manipulated by many bones, and which bone manipulates the vertex how much, it depends on these weights. Okay, we will see that thing later. The next thing is the structure that holds the skeleton. Now in our case, I am just simply creating a structure called bone, and every bone is going to have an ID. This ID is nothing but the index that it's going to be pushed when finally we will be uploading it, the bones as uniform array in our shader program. So for that, I'm having this ID. You can just simply think this ID as the index in the array. Okay, now whenever we are loading the bones, every bone they're going to have a name, so we need a field that can hold that name, and it's called name here. And also every bone, it has some offset. Suppose you have two bones, one is the parent and one is the child. So the child bone, it has its own transform with respect to the parent bone. Okay, you can think it as the local transform of that bone. Now if you want to apply the total global transform on that bone, you need that parent's transform, and you need to reverse that transform. Now in our case, this thing is going to be very simple because assimp handles all those inverting stuffs, and finally it gives you a nice matrix called offset, and we are just going to store that matrix. It's going to be enough for our project. So we are just having this offset matrix, and after that we need some children bones, because the bone is actually a tree like structure. A bone, it will have many children, that bone will have many children, and we will propagate through all those bones to find the global transforms for each bone. That's perhaps the most difficult part in this total animation stuff. And after that, I have just created an structure to hold the animation data. Now the animation data can be simply thought as some time points. Okay, and at each time points, we are simply taking the time points as float vectors, and each time points, there are some keys which represent a position, a rotation, or a scale for a particular bone. Now this track is only for a single bone. Okay, uh, apart from that, you just need the animation class, which is simply a map of all the bones with the string. Now if you don't understand what map is, it's basically a hash table. And if you really have any problem, then just go to my uh, algorithm STL algorithm series, and you will find out that what unordered map does. Okay, but basically we have the bone track for each bone, and we are just simply storing those tracks by the names of those bones. And apart from that, we also have the duration of the animation, how long that animation is, and so that we can relay through that animation. When the animation ends, we can go to the first frame and just continue doing that. So that's all about the data structures that we need, and I hope these data structures are very simple. One data structure just represents your vertexes, and you are quite familiar with uploading vertexes except these two parameters. And one data structure contains bone. This is actually a tree like structure, cause each bone will have its own children, and they will have their own children, and all bones, they need to have a offset matrix that they can use to store their global inverse transform. Okay, and then we have our animation data, which is simply declared as a track for each bone, and all the tracks, there are simply some time points that holds positions, rotations, and scales. Okay, and the positions, they are simply represented as vectors in glm, and the rotations, we are using glm quad for that, because the quaternions are very easy to be interpolated, and also the scales, they are also represented as glm vectors. So now if we just go through the simple procedure, we can see that we need a list of vertices. In our case, we are taking a vector of vertices, and we also need a vector of indices to store the indexes of those vertices. It's pretty simple in most of the indexed drawing. And then we also need a variable called bone count that will count how many bones there are present, just to be able to upload those bones in the shader. And also we are having an animation track, a blank animation track. We're calling that animation. We are having our vertex array to store the mesh inside. It's simply an unsigned int because I am not going to use a lot of classes and stuffs like that. And we also have our root bone, that is our skeleton, and this skeleton will hold all other bones, so we just need one bone called skeleton. And we also have a texture for our model to just texture it. Okay, before we do anything, we need to have the basic transformation that is provided by the model, that is the global transformation of the whole model. And you can simply get that transformation as the scene's root nodes m transformation. Okay, each node in the scene, they have their own m transformation, but we don't need all those transformations because of those offset matrix that I talked to earlier. We only need one transformation, that is our scene's root nodes transformation, and we are going to save that transformation as global inverse transformation, because we are going to take this global transformation and we are going to invert this transformation in order to convert this transformation from model space to the world space, in short. Now you can think of this situation as you are a person and you are to be placed with respect to a tree. Now you know that with respect to you where the tree is situated, but as a viewer I need to see you as you are represented as with respect to that tree. And so just in mathematics terms of matrix, to get that kind of result we just invert that matrix. So I'm just going to do that. We are just going to call glm inverse to inverse that matrix. But before we do that, we need to know how we can just take an assimp matrix and we can convert it into a glm mat4. For that I have written a very handy function called assimp to glm mat4. We will just look at the definition of that that function, and it's a very easy function. We just go through all the columns of that matrix and we fill in the rows. Okay, that's all that you need to do. Basically you just run two while loops for 0 to 4, and that is 0 1 2 and 3, and inside that for loop you just swap the x and y values. Okay, and that's it, and after that you return that matrix and you're done. So with that we have our global inverse transformation, and obviously we are going to inverse that transformation to get actual global inverse transformation. This is just a global transformation that we are getting, and then we are converting it to global inverse transformation. So this is the perhaps one of the most important steps in our code. Okay, after that we are just going to load our model. To load our model we will take the scene and the mesh that is provided by the scene, that is this mesh, and we are going to put all those values inside our vertices and the drawing sequence indexes in our indices, and the whole bone data in our skeleton data structure, and also we are going to have the bone counts. Now to simply understand how we are going to load the model, I will just explain those things a little bit later. But after we load the model, we are going to load the animation, and to load the animation we just need the scene. We are going to extract the animation data from that scene, and we have already our animation data structure, so we are just passing that animation data structure into this load model function. After that we are just creating our vertex array using our vertices and indices. We are already familiar with this, just writing a fucking mesh class and it's done. We are just using a function for that. I will explain this. And after that we are just importing the texture that is associated with the model. Now I am not going to do a very super smart material kind of importing, because you will find tons of video on how to do it. So I'm just directly importing this png file, because I know that only this texture I need to upload this texture to the to my shader program, and that's it. After that we need an identity matrix. So why we need an identity matrix? Because whenever the model you want to represent that model as a static model, right, you don't want to apply any animation, then you want that model to have an identity transform. An identity transform just simply means that you are multiplying the whole thing with 1, and that results the same thing. Okay, so you are not doing anything. For that kind of thing, you can use an identity transform. And what we are going to do is, we are going to create a vector called current pose that will hold our current pose for the time being, and we will initialize that current pose to have at least to have the number of values that is equal to the number of bones, because each bone will give us a separate matrix, and we will initialize all the matrices as identity matrix for our current pose. Okay, so this is our default state. You can think of it as the static state. And after that, we are going to create our shader. That's pretty simple as well. If you are watching this video, then you probably know how you can take a vertex shader source and a fragment shader source and create a fragment shader, create a shader program. And after our shader program is created, we will simply have our matrices. Like we will have our matrices, like we will have our projection matrix. We can use GLM perspective projection to have our projection matrix. These things are pretty much simple, but even if you don't understand how to do it, I will be giving the link of the code in description. So you can go to the GitHub and look through that code to understand whatever is happening. And also we just have the standard projection matrix, view matrix, and model matrix. And I'm just, to save the time, I'm just multiplying the view matrix and the projection matrix in order to get the view projection matrix. Okay, and these are very much self-explanatory. Now I'm not going to discuss about these things, because these things are out of the scope, and you will find tons of tutorials on these things. Okay, and for the model matrix, I'm just translating the model a little down along the y-axis, and also I am scaling the model because the model is very large. So I'm just scaling that model to 1/5 of the size in all the axes x, y, and z. So that's it. I'm just redefining the model to fit our screen. And the same thing, I'm just redefining the camera to have a perspective view. And for that, I need to pass the viewing angle, that is 75 degree for my case, and the aspect ratio of my screen, that is the window width and window height. And after that, I'm just passing the near plane distance and the far plane distance. You can see, you can think of these things as the distance, that the minimum distance from which the camera can see, and the maximum distance to which the camera can see. Okay, this is your all the things. These two things make your camera. That you have tons of tutorials on how to create a camera in C++ and opengl in the internet. And the view matrix, it's simply I'm just to create the view matrix, I'm simply looking at from this point. My camera is situated at this point, that is in -5 at z-axis and a little high at 0.2 at y-axis, and I am looking at the origin. Okay, and the third parameter is what I consider as the world stop. In my case, I am considering y-axis as the world stop, so I am giving here these values. So after that, I'm just multiplying those two matrices to get my view projection matrix. You can think this matrix as your eye into the gaming world. Okay, and I have already discussed about the model matrix. So I have all these matrices, and also I have these bones, or whatever you say, this array of bones, and I need to upload these things to my shader. So for that, I need the locations. Now many people confuse the fact that they need to have the location every frame in their program, but it's not true. Whenever you compile your program, you already have mentioned a particular static location for that variable or for that uniform in the shader. So you just need to take the location once, and you can save that location outside the for loop, just at the initializing state, and that's enough. So in our case, we are just getting the location for our view projection matrix, where we will upload our view projection matrix, and also we are getting the location for our model matrix, and we are saving that location as unsigned integer. And also we are getting the location for our bone transforms array, the array of the matrix arrays, and we are storing those at that array as bone matrix locations. And also we are getting that a uniform for our texture. Now there is a single texture, so you don't really need to have that uniform, because this uniform is defaultly bind, but still I'm going to get this uniform in case there is no error. Okay, that's all. Now after we have all these uniforms and all these matrices, Rest of the stuff is very simple. You just need a value on how much the time has passed, and in my case I prefer to change that value into seconds. So in case of SDL it gives me milliseconds, so I'm just dividing it with 1000 to get the value in seconds. And obviously this is an integer, so I need to cast it to float first to get the decimal places right. And after that I'm calling this function. I will discuss this function a little bit later. It's called get pose, and what it will do is it will take our animation, take our skeleton, and take the amount of time that has passed, and it will fill all those, it will consider all those informations, and then it will calculate the new pose, and it will fill that pose into our current pose array. And it will have a default pose to start with. In our case we are just passing that identity matrix as the default pose from where it's going to start. And after that to calculate each matrix position, I just told you earlier that we need that global inverse transform that we got there, and we're just passing that to it. Okay, we will be discussing about this thing a little bit later. So once we have that, we have this function run every frame. It will take the animation time and it will get the pose in our current poses vector. And now from this current poses vector, what we can do is we can upload these current poses to our shader, and we can do stuffs. So before that I'm just going to simply explain you how I'm just drawing the whole thing. So first of all I'm just clearing the whole screen, the color buffer bit and the depth buffer bit. To do that you need to first enable this depth buffer bit, and color buffer bit is already enabled. Then I am just binding my shader. Okay, so I am calling gl use program on my shader. I'm just taking these things as unsigned integers, so I just can directly call these functions from you. And then I'm just uploading all my matrices. To upload my matrix I'm passing that position. So first I am uploading my view projection matrix to the view projection matrix location using gl uniform matrix 4fv. And I don't want to normalize those matrices, so I am just pressing gl false here. And this parameter, the second parameter, it denotes how many matrices that you want to pass. In our case our projection matrix and our model matrix, they are only one in size, so we will have one here. But in case of our pose have bone count number of poses. We can also say current poses dot size here. But I have just passed the bone count here because these many number of bones are present in our current poses. And you just provide all the value pointers, glm value pointers to all those matrices. And in case of an array of matrix, you just give the value pointer to the first element of the matrix. That's it. And this is enough to upload all the uniforms, the uniform matrices that we want to upload. And to use glm value pointer, you need let's say you need the header file called glm/gtc/type ptr. Now this type ptr.hpp, it contains the function that is called a glm value ptr, and it's quite handy. But even if you don't want to use this function, just give the reference to the raw data. It's going to be enough. Okay, even if I show you this function, what this function does, this function is very simple. It just returns the first variable's address. Okay, so it's very simple from that perspective. After that I am just binding my VAO where my mesh or the model, whatever you say, is stored. And then I am binding the texture. I am activating the first texture slot. I am binding that my diffuse texture to my 2D texture. And also I am informing that the first location, the 0th location, is enabled using the integer location that I have retrieved earlier for my texture. Okay, and after that I'm just calling gl draw arrays. It's a very simple function. As my VO is bound, it will draw my VO here, and I want to draw everything in triangles because we have triangulated all the faces. And after that I'm just passing the second parameter as how many vertices are present there, how many points I'm going to draw, and that is going to be decided by indices dot size. And after that I am just passing here that how to treat those indices. In our case our indices are gl unsigned int, and then I'm passing 0. This is very standard function. You have already, if you are watching this video, you know all these steps. Okay, so I'm not going to do so many things, and after that we are just swapping that window. So this is the basic framework of how our implementation is going to work. Now we are going to get to the actual part, that is how we are going to load those animations and how we are going to play those animations. So for that we will start by looking at the function load model. So if we open this load model function, if we open this function, you can see that it is taking the scene, it is taking the mesh, and then it is taking a reference to our output vertices, and it is taking a reference to our output indices, and it is also taking our reference to our output skeleton. Now remember, the only way I have to pass one bone, because one bone it has its children and it will have their children, so just one bone is enough. And also we have the bone count here, that is n bone count here. So first of all we are just emptying our vertices and the indices. Now the mesh, it has a number called m num vertices that denotes how many vertices are present there. So we are just going to run a for loop saying I is equals to 0 and I is less than m num vertices, and we are just incrementing I. Now in each for loop we are going to declare a vertex. Okay, and first of all we are going to retrieve the position, and you can simply get the position by giving the index to m vertices and then xyz to the for the xyz value of the vector, and I am storing the whole thing in a GLM vector. And after storing that value, I am assigning that value to the position first. The same thing goes for normals. Instead of vertices, this time I am using m normals and I am giving the indexes I, and thus we have the normals. And the same thing goes for UVs, but in case of UVs we are just getting a vector, so I am just declaring another vector here, the GLM vector, and I am getting the x coordinate and a y coordinate from m texture codes array in the mesh. And we are getting the first texture coordinates, because a model can have multiple texture coordinates, and I am just interested in the first array, first index of the texture coordinates, and we are also giving that I there. And then we are getting the x value and the y value, and we are saving that vector, and after that we are setting that UV of the vector. And for this loop we are just going to set all the bone IDs to 0 and all the bone weights to 0. Okay, and all the 5 things of our mesh is basically set, so all the vertices. So I will just have all those values pushed to our vertices output to have our vertices output to hold all those vertices. Now this is the first round of getting the values. I have the position, I have the normal, I have the UV coordinates, but I still don't have the IDs of the bones and the weights of the bones for the vertices. So for that I'm going to do a little trick. This trick is going to be for easy than other tricks, and that is going to involve an unordered map. Now why I'm using an unordered map? Because it's very lazy to use actually. So I will have an unordered map of let's say it will have the and the mapping, that is the hash table, will have a name for each bone, and for we accessing that name, you can think this as a table. For each name in the table we are storing an integer that represents to the ID of that bone, and we are also storing a matrix that represents to the offset of the bone. If we have seen earlier, then we are just storing that ID and that offset depending on the name. That's simple as that. And if you don't understand how unordered maps or vectors work, I highly suggest you that you watch my STL series. It's going to give you a clear idea on how you can use unordered maps or vectors in your projects, and they are going to save you a lot of time actually. So let's get back to it. So that's what our bone info unordered map is. And also we're going to have a vector called bone counts. Now why bone counts? Because for let's say we have every vertex, and for every vertex we are adding one after another bone. So for the first bone we are putting it at the x index, and then for the second bone we are putting that bone in the y index, and then so on. But we need a count to understand whether we are putting that thing in x index or y index or z index or w index. For that I'm just getting a vector of another ints called bone counts, and this is not that n bone counts that we are passing. Okay, so keep thinking is that, but this is just the number of bones for each vertex. Okay, we are just having the bone counts for each vertex, and so that I am just resizing my whole vector with the initializing value 0, just like we resized our current pose, and the size of this vector is just equal to the number of vertices that we have in our vertex vector. Okay, and uh, we are assigning the number of bones that that number of bones that we passed in our function earlier. Here in here we have passed the number of bones, and we are assigning the number of bones. We can simply get the number of bones by calling mesh n number of bones. N number of bones represents how many numbers of bones are present there. Okay, num bones. So after we have these things, and we know that these many bones are present here, so I will run another loop. In this case I will run the loop from 0 to number of bones, and I will every time increment that id of the I to get that bone and put those informations into these blank spaces. Okay, and we already have these two utilities to help us out. Okay, so first of all, what we are going to do is we are going to retrieve that bone. Now every bone is represented in assimp as ai bone pointer. So we will take a bone pointer and we will simply get the bone by referencing the m bones array by the index for that bone. And now I have the bone that is mentioned in assimp. Now first thing, I will get the offset matrix that is just magically provided by assimp to you, and you don't have to think of anything else. So just get that offset matrix. We will use our handy function called assimp to glm matrix, and we convert this matrix in glm. All we are doing is we are just the matrix presented as in row measure order, and we are converting those to column measure order. That's it. And after that we are getting the name of the bone, and we are getting this a c star function. We use the c star function to get the string out of that bone, the c string, that is the const char version, and we are just setting the index of the bone. Okay, the number of the bone and the matrix, offset matrix of the bone, into the bone info table by the name, so that we can just say that bone info root, and then we can get the value as this one and this one. Okay, for that we have this unordered map or the hash table, whatever you like to say. For that we have this unordered map or hash table. After that we are going to get the number of how many bones are present there. Now for each bone there is a field called m num weights that represents how many vertices are affected by that bones. In our case we will be running another loop, and loop that is inside this first loop for each bone, and for each bone I'm going to run this loop. So for int j equals to 0, j is less than the bone's number of weights, that is how many, the number of vertices that are being affected by the bone, I will increment the j. And now we are going to do our simple trick. We are going to get the id of the vertex, okay, by simply calling bone m weights, giving that index. And m weights will has two fields. One is the vertex id, and the second field is the weight that is associated with that id. So we will get the id as an unsigned integer, and we will get the weight as the weight variable. Okay, and by the way, uint is not available in your program. I have just simply defined as a type def unsigned integer as uint, and also I have defined type def unsigned character as byte. So keep this thing in mind. So that we have the id and the weight for that particular series. And now I will have my bone count vector, and I will find the particular bone of that vector. In suppose my id has come here as 2, so I will take the second position of that vector, which is already 0 as initialized, and I will increment it. Okay, so I will know exactly that the second vertex, it has one bone, and the next time when I visit the second vertex, I will increment it once again, so it will say that my second vertex has 3 bones. Okay, so what's the benefit of that? I can simply switch this variable, that is bone counts id, for that vertex that we have already got here, and I can put a case, that is whether this value is 1, 2 or 3 or 4, and depending on that I know that this vertex has going to be have 1 bone, 2 bones, 3 bones and 4 bones. Now for each cases, what I am going to do is I am going to take my vertex array that I had previously left these fields empty, and now I am going to fill those fields, as first of all the bone id, and the id is simply not just the id of that bone in the this bone id loop. I am also putting that id inside this bone info, so keep this thing in mind. This is for the for making that skeleton, okay, and this is for the vertex data, so don't confuse both things. In both cases we have to pass this I. This I is very important. So, and also we are just passing, we have gotten the weight here, as you can see, for that bone, we are just passing that weight as the bone weights value. And now depending on 1, 2, 3 or 4, we are passing those values in x, y, z or w, and thus we are just filling all these empty spaces in our vertex array, and that's sufficient to do all our calculations. So after the switch statements have broken, we will we will end our for loop for the j, that is for every vertex present in that bone, and then this for loop is for the final for loop will exit, which is for every bone, okay. And thus we will have our vertex information, that vertex is output array completely ready. So our vertex information is ready to be processed. Now the second thing is I'm going to another thing that we have to consider is that the weights, they sometimes don't add up to 1, okay. So I just have to keep that in mind. And these things is this is the most simplest thing to do. We just run a for loop for each vertex in that vertices array, and in that for loop you just take the bone weight and you add all the weights, that is x, y, z and w, the weight of the 4 bones. And if the total weight is greater than 0, then you just divide every weight by the total weight and assign that value to the new bone weight. That's it. In this case I am creating a new vector with all the weights divided by the total weight, and the total weight is nothing but the summation of all the weights that are present here, the dot x dot x dot y dot z dot w. That's it. And this is just so that every bone has a total weight of 1 for all the bones that are affecting a vertex, and that's it. And after that I'm going to load the indexes array, because we have already fully processed our vertex array, okay, vertex output array. The next array that we are going to process is our indexes, that which vertex we need to use in order to draw our geometry. And for that I'm going to loop through the number of faces. I'm going to set the value of I to 0 to the number of faces that are present in the mesh, and then I'm going to loop through all the faces. I can simply get the reference of the face by AI face reference, and for each face what I'm going to do is I'm going to run another loop is that is from 0 to the number of indices that are present in this space. Now in this case we will always have the value of j from 0 to 3 because the simple fact that we have triangulated that our whole mesh in the beginning, and a triangle has only 3 indexes, that is 0, 1 and 2. So those 3 indexes, we will just push those things in indexes output. You will find tons of tutorials that are going to do these same things, so it's not that very difficult. And after that we have our index array and we have our vertex array, and also we know how many bones are present here. And also we have created a data structure called bone info that has a table of all the offset matrices and all the indexes, that I values of all the bones, along with mapped to the names, okay. And we will use this information to construct our skeleton. This is going to be a little bit harder because we are going to use a recursive function. And by the way, this is being done on a single mesh, but if you want to do this on a multiple mesh basis, then you just need 2 simple hacks. First of all, you just need and offset bone id and offset vertex id and offset index id, 3 things. So first of all, you have processed a mesh, then you just increment the vertex id from the next vertex, that whenever for the next mesh I am counting the vertexes, I will add that vertex count to that. And I will do the same things for the bone counts. I will add that bone count, or I will add that index count to that index, and that way I can have all that recursive mesh loading kind of thing that you can find in opengl learn opengl.org or something like that website. And you just, for that you just need to have the count of the bones and the vertexes and the indexes that are present there. That's all that you need to do. But for now we are going to create our skeleton. To create our skeleton, we will call a recursive function. What is a recursive function? A recursive function is a function that calls itself, and I will call this function as read skeleton, and it will store all the values in our skeleton array, that skeleton tree that we are passing as output to our main function, that is our load model function. Here you can see our load model function has this single bone as skeleton output. You will just find these things in a minute. And I'm also passing the root node of my scene. That's why I took the scene, because till this point we haven't used the scene yet, but we need this root node of the scene in order to construct this skeletal output. And also we need this bone info, the table that the hash table that we created here in the bones loop while creating, by providing the id of that bone and the offset matrix of the bone. And this is not very difficult actually. You will see that this function is actually very simple. So let's just open this function. Now this function, it typically depends boolean, depending on which I will understand whether I have to exit the recursion stack or not. Okay, so first of all, I have that table, bone info table here, and I will get I have the root node here. Okay, so let's think this as for the root node. So first of all, I will check whether the root node is present in our bones array. Now your model, it will have many things, like your model is your mesh is present there. There might be cameras, there might be lights, and there might be so on. But the light is not your bone, and the other things, they are not also your bones. So you have to be careful. You have to be very careful that you are passing the bones. Okay, so for that I am just checking whether the name of that bone that is given by the node, that node mname.cstr, you are already familiar with that. This is a very typically assimp like syntax, and I will find that name inside our table. And if that's equal to the end of my table, that means if the bone is not present here, you can also write you can just also create a for loop here and check that thing. But already our maps give us this functionality, so why not use these things, because this function is going to take constant time to do the thing, even faster than a for loop. Okay, so if the value is present, so if the bone that I have been looking, that is provided by the node, is also present in my table, so I will I just hit the jackpot. So what I will do, I will take my bone that is given to this this read skeleton function, our output array, our output bone, and I will set the name of the bone to the name of the bone that is present by the node, the name of the node, and the id to the output, to the table's id, the table's the first element of the table has an integer, that id, that from that for loop I will put it as the bone's id, and the offset, the second matrix from that for loop, if you remember earlier, and I will put that in the second position. So this simply means that if if I can find that bone inside the bone presented by this AI node, if that bone is present in my bone table, if that's the case, then just fill the name, id, and the offset. And once you have done that, for every children bone of that node, so I will just call, if I equals to 0, I is less than m num children. This is a very typical assimp like structure syntax. If you have been going through this much time, then you already know that what this represents. And I will create a new bone for the child. For every children of the node, I will create a new child bone, and I will pass that child bone to the to my recursion function read skeleton. And also I will pass the child of that node, the ith child of that node, and I will also pass the whole table, so that it can do the same procedure, this procedure, for also all the child nodes of that node. That means I have passed the root node here first, and then for every it will fill up that information for all the values that are present in root node, and then for every child of that root node, it's going to create a new bone, and it's going to fill those information of that new bone inside that child's. And the final thing, for my bones, the original root bone that I have, I will put that new child bone inside the children array of that my bone. Now if you can remember, my bone, it also has a array of bones, a bone that has an array of bones, a vector of bones called children. And this is how we can typically we can create a tree of bones. Okay, we have a tree of bones, and this is how you just simply create a tree, okay, in computer science. And once everything is done, I have processed the bone, and I have processed the children of that bone, and the children, they will also process their children, and those children, they will also process their children, and we have done. So we will return true, saying that we have successfully read all the values. Okay, now in case our assumption is fail, that means the node that we are looking at doesn't belong to the category where our actual bones lies. The node is not a bone, that is that the node is camera or anything else, the root node. In that case, we might find that bone to, because we are passing the root node, we might find the actual the bone data for in a children of that node. So what we will do is, if that bone is not present, so we will just look through all the children of that bone again, but this is when the children are found. And in this case, I will call the same function. The only difference is that I was creating a new bone for the children that time, but this time I will pass the original bone to the children, because I know that this bone is not yet processed. So I will just pass that bone to the children, and this function will magically do the stuff. And also I will put this thing in if. So whenever I have found that bone, I will just return. Okay, return means I will whenever the true is returned, that means that I am out of that loop. And this read skeleton function, if you remember, it returns true whenever it finds the it finds and then calculates successfully all the bones. Okay, so in this case, if the read bone function returns true, that means all the bones have been already initialized. So I will just return true and exit from that function, also from that for loop, so that no further children are processed. Okay, because the next children might be the camera or the lights. Okay, and if all these things fail, then I will just simply going to return false, and this will take care of all those cameras and things that I was talking about. So this function, it looks a little weird, but if you just debug this whole function, how it's behaving, then it's going to be very simple. And actually recursive functions are very useful in this kind of messy situations when you don't know what's the depth of the tree. And in particular this scenario, and the thing that we are doing is called as a depth first search. Okay, so we are just doing a depth first search here. If you don't know that what we are actually doing here, so we are just doing a depth first search here. Now, because this function, it will call its children, then it will call its children, and then it will call its children. So the last child, when it's done, then it will come to the next child, and so on. So this kind of searching is called depth first search. If you want to understand more about depth first search, just search about depth first search in YouTube, or you can comment about how we do typically depth first search, and then I will try to make a video on depth first search. But this is how basically your all the informations of your bone and its children are going to be put inside your skeleton, and finally we will have our skeleton ready. That is, we will get our skeleton output from the root node and the bone information table that we created. So the first part is complete, that is, we have successfully created our mesh array. Okay, so our meshes, we have successfully extracted our vertices, our indices, our skeleton, and our bone count. Now we need to extract our animation. Okay, to load the animation, we are simply passing the scene and passing our animation struct where we will load that animation. And first of all, we are the animations in assimp are treated as AI animation. So we are extracting an AI animation pointer called anim from our scene, and it's located in our scene's animations array. We are taking the first animation out of the array, and that animation holds a quite some things. The first thing is the am ticks per second. So am ticks per second, it might be 0. If it's a 0, then set it to 1. Otherwise just set it to ticks per second. It just means that how many ticks are counted in 1 second for that animation. And next of all, we are putting our animations duration, and to get the duration, we just take the animations duration and we multiply that with the animations ticks per second. And then we are just making our bone transform map empty. And now we are looping through all the channels that are provided by the animations, and it's the number of animation channels are m channels. Now for each bone there is a one channel, and that channel represents all the animations for that very bone. Now to get that channel, we are just taking a node anim pointer called channel, and we are getting the ith channel in this loop, and then we are creating a bone transformation track called track. And now each channel they have a lot of keys, and the keys represent as keyframes for the animation. There are position keys, there are rotation keys, and there are scaling keys. So for each of them, that is for just channel m num position keys, we are going to extract all the positions, and we are going to extract all the rotations for m rotation keys, and for the num m scale keys we are going to extract all the scalings. And assimp has this kind of typical naming scheme. You have already seen this kind of naming, so I'm not going through in details, but you can see it quite clearly. And we are looping through all the keys, and we are putting the all the keys, they have two values. One is the timestamp where the key is taken, and another value is the value of the key itself. So we are just putting the timestamps into our timestamps. For positions we are putting them into position timestamps, for rotation we are putting them into the rotation timestamps, and for scales we are putting them into the scale timestamps. As well as for the positions and rotations and the scales, we are putting the positions, rotations, and the scales. Now positions and scales, they are presented in GLM, then in assimp vectors. So we are just converting the assimps to GLM vectors with our handy function, and it's very simple. We are just taking the x and y, x, y, and z values, and we are creating a new vector and returning that. And for converting an assimp quaternion rotation to a GLM quaternion rotations, we are using quaternions here, by the way, not Euler rotations or any kind of other rotations, because it's very easy to interpolate between two quaternion rotations. It's not very easy to interpolate between two Euler rotations, and you will end up with weird kind of rotations. But in case of quaternion rotations, you just simply multiply those things. And in our case we have GLM, so GLM provides us with handy functions that can handle those interpolations for us, so we will not be even bothering about that thing. And just simply creating a quaternion, we are just creating a quaternion called q, and then we are assigning the four values of a quaternion, x, y, z, and w, from the assimp quaternion, and then we are returning that quaternion. And to use the quaternion, you need glm gtc / quaternion .hpp and glm gtx / quaternion .htpp. So yeah, that's for the quaternions, and this is how we are typically loading the positions, the rotations, and the scales into our animation structure, that is our track for each bone. And finally in the bone in the bone transforms map, we are putting the track with the keys of the name of the bone. So for each name in the bone transform track, we have the correspondent track for that bone. Like for the let's say for the hip bone, we have all the animations for the hip. For the hand bone, when the name is hand, then we have all the animations for the hand, and so on. And this is being done for each bone, and every bone is represented as a channel, I have already told you. And after that there is nothing more. If your function is returning the animation then structure, then return it. I'm not returning it, I'm just taking it as a value argument, so it's being modified here. Okay, I'm not copying that argument. So yeah, after that we have done this, and now it comes to creating our vertex array, which we have done and seen in many kinds of videos. If you're watching these videos, then I think that you can create a vertex array very easily, but there is some difference, and I am going through that. Creating a vertex array, you already know how to create a vertex array. You just take a vertex array into three integers for a vertex array, a vertex buffer, and an index buffer. So first you just generate those arrays and the buffers, and after generation you just bind that vertex array, you just bind that vertex buffer for GL array buffer, and then you push all the vertices that I already get into the buffer as data. You have already seen too many tutorials on this, so it's going to be very easy. And I'm just going to declare this as static draw because I'm not going to modify these values. Now for every attribute that are present in these vertices, that is that position, normal, UV coordinates, bone weights and bone IDs, I am going to enable the vertex attribute pointer once attribute array. For 0 I will store the position here, and for 1 I will store the normal, for 2 I will store the UV, for 3 I will store the IDs, and for 4 I will store the weights. Now these three are typically same as others, and also you don't need to enable these for every time in your loop. You just can bind this vertex array, and before unbinding it, you just need to enable this thing once, and it will, whenever you are going to bind this vertex array next time, they will be all automatically bind, so you don't need to specify those things and waste performance. So how we are going to define those things? Very simple. We will call GL vertex attribute pointer. The first parameter is the location, that is the 0th location, and I am passing a vector of 3 floats. So this is 3, the number of items present, the kind of value. In our vectors all have the GL float value, and we don't want to normalize those vectors, that is why we don't want those vectors to be from 0 to 1, so we will pass 0 GL false here. And then the size of every vertex, that is the stride of the vertex, and for that we will just pass size of vertex. And for the next thing is the offset for every position in that array. So for that we will just we will use the offset of function that is provided by cstdlib, and using the cstdlib offset function, we will pass the offset of the position, vertex, normal, bone IDs and bone weights, and we will convert these to GL floats. But if you are not familiar with using this, then you can just simply say 3 into size of floats, 4 into size 3 into 5 size of floats for this, 3 in, then 6 into size of floats for this, then 0 into 5 size of floats for this, 3 into 5 size of floats for this, 6 into 5 size of floats for this, and then 8 into size of floats for this, and so on. Okay, you get, then you will have 4 such things. So just these are the locations, and these are the number of floats that are present, and we are sending all the floats here, so it's nothing that fancy. Then we are just going to bind that index buffer, and we are going to upload the indexes the same way that we have uploaded the vertices, but in this case we are going to upload those indices into the element array buffer, and after that we are just going to unbind our vertex array, and that's done. And you have seen at least thousands of tutorials explaining this thing, so I'm not going to explain these things in very detail. Okay, and after everything is done, I'm just unbinding that buffer and I am returning the view. The next thing is going to we are going to create a texture, that is, so I'm using stbi image. This is the header only file to load images into memory, and you will see tons of tutorials on how to import an texture, and how to create a texture, and all the textures in OpenGL's perspective, they are all presented as unsigned integers. Okay, and I am setting the filters here, and then I am finally setting the values and the stuff. So this function, I don't think that I need to explain this thing to you, how to create a texture. And now the main thing, the Gatepost function. The Gatepost function takes the animation track, takes my skeleton, takes the time that has been passed, and depending on that, it creates our current pose, that is our output here. And to create that current pose, it needs its parents transform, where we have passed in identity matrix for the beginning bone, that is the first bone, and that is the root bone, the root joint. And also we need the global inverse transform that we have loaded earlier. Okay, so get pose is very simple, but before that we need to understand one thing, that is the get time fraction function. Now what get time function does, it gets the times arrays. Okay, if you see an animation track, if you want to notice, is simply an array of times, array of floats, time points. Suppose we have a point at 0.25 second, then we have a point at 0.50 second. So these are just the time points. Okay, the time of the keyframe. Let me go to the function. So this takes the whole time point functions, and it takes the current time that has been passed. I have written dt here, but it doesn't make any sense. This is the elapsed time, and all it does, it finds that how much, which frames that it need to pass. Okay, now it's quite confusing to you, so let's get it very simple. So first of all, we have let's say 4 time points. Okay, and our time is greater than the third time point. That is, our time is suppose 0.8, and the third time point is 0.6, and the fourth time point is 0.8, 0.9. So for the third term, we have unassigned integer segment representing to the index of the time, and while I'm not getting the time point, I'm just incrementing that segment. Okay, so I'm just finding the index in this vector which the current time frames belongs to. Okay, now once I have got that segment, okay, once I have got that segment number, that's the first parameter. That's my get time frame function returns, because it returns a pair. A pair means two values. One is an unsigned integer, that is the index in that array, and the second is the fraction, that is how much time has been passed in a fraction. That means in scale of 0 to 1 from previous frame to next frame. That is, I'm just trying to find the value for which I'm just going to interpolate the animation, and for that I'm just going to take the previous frame, that is times segment -1, and the current frame, that is time segment, and I'm just going to call those as start time and the end time, and the fraction is simply the time that has been passed minus the start time divided by the end time minus the start time. Well, this is the whole duration, and this is the temporary duration, and as a result this is going to give me a fraction between 0 to 1. Okay, so this is the second thing, the fraction. Now the get pose is very simple. It just takes the animation track for every bone. Okay, because I am just calling Gatepost function. This is also a recursive function. So first I will call this function for the root bone, then all its children, and then those function calls will call the Gatepost function for their children. Okay, so first of all, I am getting the animation track for the particular bone we are currently at in our skeleton. So we will get the name of the skeleton, and as you can remember, these tracks, they are also named after the name of the bone. So I will get the track here, and after that I will just simply divide the dt, that this function, to that with the total duration, so that if the time exceeds the duration, it will be cut to the remainder of that duration. Now in case of a floating point division, you just can't simply use modulus sign, so you can use f mod, that is provided by C maths, perhaps C maths library, and you can use this simple functions to get this value modulus between, and have this value always less than the duration. Okay, and after that I'm going to get the values from the time points for our position timestamps using the dt, because I'm just going to pass that position timestamps into dt. I'm going to get the fp, that is the index of the position timestamp, that is the fp dot first, and also the fraction, that is fp dot second. And what I will do is I will get the first position, the position of the previous time frame, and the position of the next frame by simply in accessing the previous frame position and the next frame position, just like we accessed here the segment numbers. From the segment number, it represents the first here. Okay, so we will get the previous position, the next position, and then we will simply get the actual position by calling this function glm mix, which mixes two position, which linearly interpolates between two vectors, and we will give position 1, which linearly interpolates between two vectors, and we will just simply give position 1 and position 2, and the fraction, that is between 0 and 1, to how much interpolate between these two positions, and we will get in middle position for the position. So that even if we have 4 time frames or 2 time frames, and our time is exactly in middle of those time frames, I will get 50% of that position and 50% of this position, and a combined position, like that. So for that I am going to use glm mix, and you can just go through other documents and tutorials, and they will show you how you can linearly interpolate, but it's just so easy to do, and that you don't need to actually do it. You can just simply call glm mix and it will do that. Okay, The same thing goes for rotations. You just get the previous rotation and the next rotation. First you get the rotation time frame from the rotation timestamps, okay, and the rotation what they call it, rotation fraction, time fraction or whatever, and you get the previous rotation and the next rotation, and you simply use glm slat, and you simply use glm slat. Slat means some smooth linear interpolation. All it does is just some trivial quaternion multiplication. If you are interested, there are tons of tutorials on how you can interpolate between two quaternions, and I don't want to waste time, so and I have this function available here, so I will use this function to get the intermediate rotation. It's just same as mix, even you can use mix here and it will work fine, I guess. Okay, and the same thing goes for the scale. So now I have the exact rotation, the position and the scale for all the three, all for that particular times moment that I need for that bone. Okay, and with these three informations, now what I will do, I will create matrices. Okay, so I will create one matrix for the position and set it as identity matrix, and one matrix for scale and set it as identity matrix, and I will translate my position matrix with the position that I have recently found in this position, and I will rotate, and I will also create a rotation matrix using glm2 mat4 function and pass this our quaternion here, and our quaternion will be converted into rotation thanks to this magic function. And then I will create our scale matrix by providing the scale vector into the function glm scale and our scale matrix. So now I have three matrices that represents my position, my scale and my rotation, that position matrix, scale matrix and rotation matrix. Now to find the bone's model matrix, or in layman's term the local transform of that bone, I will just simply multiply the position matrix, the rotation matrix and the scale matrix, and that will give me the local transform of that bone. Now once I have the local transform of that bone, to find its global transform, all I need to do is I need to multiply that bone with its parents transform. Now this function is designed as it will first calculate the transform of the root bone, then it will calculate the transform with its child bone. So whether so in which branch you are, suppose you are the child of a child, so the child will have its transform dependent on that parents transform. So actually this global transform will change the parents transform like this. Suppose you have a parent 1, so you will just have like this will change for the third child. It will actually calculate the value like this: parent transform 1 into parent transform 2 for the second child, and then its local transform, and that will be passed to fourth child as parent transform 1 into parent transform 2 into parent transform 3 and parent transform 4 and so on. This is the beauty of using recursive functions. Okay, they are very easy to use and they are very skillful. And now that I have this global transform, I will take my output array, and in that output array I will find the id of that bone, that particular bone that I am interested in, that is which is the what is the location of that bone, and in that array I will put this value, the global inverse transform, into the global transform of that bone and also into the offset of that bone. Now this offset represents that bone's inverse transform. Okay, and that is provided to you by assimp, and we had gone through all those things to save our time here. Okay, so it just and this global inverse transform, this is just supplied once, this is just getting once, you just get the transform of the root node and you invert it. Okay, and that's it. And then for every child, and then for every child, sorry, I was just running a little bit. So, and then for every child of the skeleton, I will pass that child bone and the animation and also the same output array, and the same time this the global transform that I just calculated for this bone, because this transform is going to be the parents transform. For the root node, the parents transform was identity matrix, but for its children, the parent transform will be the global transform of that node. Okay, and then finally our global inverse transform, that is a global transform that we just got at the beginning of our video. So if you just forget what it is, just go to the beginning of the video and see it, and we're done. Okay, we don't need to see out. Okay, so with that we have successfully filled all, traversed to all the bones of our skeleton, and we have filled our vector, because the number of elements that are present in our vector is equal to the number of bones that are present in our tree, the skeleton tree. This is also a very interesting example on how you can convert let's say a tree into a array. Okay, this is how you do it basically. So once that has been done, you have executed the get post function successfully, and you have all that remains is drawing that I have already mentioned you, and you are done doing it. Congratulations, you have done skeletal animation. But one thing, you just need to know what the shader should look like, right? So in so first, the only thing that we need to actually know about this whole shader program is our vertex shader. So I will just go through the vertex shader source code in short. So first of all, we need all the attributes that are given to the shader, that is our position, our normal, our UV, and the two more attributes that are presented here. One is bone IDs and one is bone weights, and they are given as vec force. Okay, and the output, it will have the texture coordinate, of course, the normal, of course, and for our lighting calculations, and this one just ignore it. It was for the debugging purpose. And we'll upload our bones, okay, as a uniform of matrices, and here we will have a max matrix count. It doesn't matter how much what number you put here, but just keep in mind that the number of bones of your matrices, the number of matrices that you pass by current pose should not exceed this number. Okay, and then you have this view projection matrix for the particular bone, for the particular model, by that is the eye, or the eye of the camera. Okay, and the model matrix. So the thing is simple, you just remove all these things. So the thing is simple, you just if you want to normalize the bone weights, then you can do the normalization here, but I'm not going to do the normalization here. All you need is a bone transform matrix. I am just setting this matrix as a 0 matrix. Okay, and then for each vertex id, I am going to grab the transformation from that array. Okay, and obviously these are in floats, so I will have to cast this first in ints, and then I will multiply this with the associative weight of that bone. Okay, so I will do this for x1, then for y, for z, and for w, and the each transformation I will accumulate that or add that value to our final bone transform, and then we will have our bone transform matrix ready. And the only thing that we are going to do that is different is we are going to create a new position. That position will be the original position converted into vec4, obviously, and multiplied with the bone transform. And we will, instead of using this position right here, instead of using this position, we will be using this position for all other calculations. Like our GL position will be our view projection matrix into model matrix into position, and our other values like v pause here for our lighting calculations will be this. Okay, model matrix into, actually you don't need to give this thing. Okay, just forget it, this is enough. Okay, and then you have the texture coordinates as uv, and for the normal I'm just transposing the inverse of the model matrix times the bone transformation. Okay, and times the normals. It's just how it works, I guess. And then we have this, we're normalizing the normal and setting that normal, and after that we are just getting a simple diffuse lighting calculation depending on this light position. You will just find tons of tutorials on what these fucking things does, so you just don't need to worry about these things. Okay, just you just can the only thing that you need to worry about is this part. Okay, and we're done basically. And if you have any, just you don't understand what is happening, just go to the link that I have given in the description of the video, and you will get the full source code. You will understand once you just go through it. Yeah. Now if we run this program, we will see that indeed our model is actually being animated quite perfectly. And that's it for today, guys. So hope you have enjoyed this video and somewhat find some knowledge inside this video. If that's the case, then please hit a like. It means a lot to me, and thank you very much.